Hi guys, welcome to chapter 23, the evolution of populations. I'm going to do this chapter in two sections. The first of which we will review and introduce Hardy-Weinberg principle and equations, and in the second we will talk more natural selection and the different types of selection and effects that go with it. So to get started, let's review. This is the smallest unit of evolution. Natural selection acts on individuals, but only populations evolve. Genetic variations in populations can contribute to evolution. Microevolution is a change in allele frequencies in a population over generations. Two processes, mutation and sexual reproduction, both produce the variation in gene pools that contribute to the difference among individuals. Okay? Speaking on genetic variation, this figure here, which is located on page 469, is an example of non-heritable variation. These caterpillars of the moth Nemorea arizonia owe their different appearances to chemicals in their diet, not to their genotypes. Caterpillars raised on a diet of oak flowers resemble the flower, whereas their siblings raised on oak leaves resemble oak twigs. So this is an example of non-genetic. The genetics don't play a factor in their differing phenotypes, the different outward appearances, but instead the environment. And such is also true in humans. Environment plays a large role in what traits, behaviors, and physical appearances are displayed. Population geneticists measure polymorphisms in a population by determining the amount of heterozygosity at the gene and molecular levels. Average heterozygosity measures the average percent of loci that are heterozygous in a population. Most species exhibit geographic variation differences between gene pools of separate populations or population subgroups. Some examples of geographic variation occur as a cline, which is a graded change in a trait along a geographic axis. Okay, here's an example of a cline. This image, if you want to look at it closer, is on page 470. Alright, this is an example showing a cline determined by temperature. In the mummichock fish, the frequency of the specific allele being studied for the enzyme lactate dehydrogenase B, which functions in the fish's metabolism, decreases in fish sampled from Maine to Georgia. Alright, the allele codes for a form of the enzyme that is a better catalyst in cold water than the other variations of the enzyme. Individuals with this allele can swim faster in cold water than individuals with other alleles. So, this allele, LDH-BB, alright, that's the allele in question. It is found much more frequently in cold water than in the same fish found in warm water. So, going down the coastline from Maine to Georgia, this cline is showing the change in the frequency of this allele based on the latitude. Clearly, the optimum temperature for this allele's functioning on that enzyme is greatest at or between latitude, say, 41 to 37. Alright? The coldest above that, the allele has a small effect, and then warmer, the allele has also a smaller effect. It doesn't make as big of a difference in how the fish functions. Okay? Alright, mutations are changes in the nucleotide sequence of DNA. Mutations cause new genes and alleles to arise. Only mutations in cells that produce gametes can be passed to their offspring. A point mutation is a change in one base in a gene. So specifically switching one point in that genetic sequence. The effects of point mutations can vary. Mutations in non-coding regions of DNA are often harmless. Mutations in a gene might not affect protein production because of the redundancy in the genetic code. Mutations that result in a change in protein production are often harmful. Mutations that result in a change in protein production can sometimes increase the fitness of the organisms in its environment. In those non-coding regions, mutations often don't change something that is going to affect the survival or the ability to survive. However, those that occur in a section that codes for proteins can and often is harmful to that organism. However, there are some that can cause an increase in the fitness of the organism in that environment. And we'll see some examples of that in just a second. Okay? Mutations that alter gene or chromosome number or sequence. So chromosomal mutations that delete, disrupt, or rearrange many loci are typically harmful. Mutation rates are low in animals and plants. Mutation rates are often lower in prokaryotes and higher in viruses. Sexual reproduction can shuffle existing alleles into new combinations. In organisms that reproduce sexually, recombination of alleles is more important than mutation in producing the genetic differences that make adaptation possible. So recombination of alleles is a more important form of creating genetic variation and genetic difference than those mutations. Relying solely on mutation for genetic difference for adaptation is not as reliable nor sufficient. Alright. Hardy-Weinberg equation tests whether a sexually reproducing population is evolving. A population is a localized group of individuals, a species in an area, that's capable of interbreeding and producing fertile offspring. A gene pool consists of all the alleles for all the loci in a population. A locus is fixed if all individuals in a population are homozygous for the same allele. Hardy-Weinberg equation. The frequency of an allele in a population can be calculated. If there are two alleles at a locus, P and Q are used to represent their frequencies. The frequency of all alleles in a population will add up to 1. So P plus Q equals 1. Hardy-Weinberg principle describes an ideal population that is not evolving. The closer a population is to the criteria of Hardy-Weinberg principle, the more stable the population is likely to be. Calculating genotype frequencies, the equation is P squared plus 2PQ plus Q squared equals 1, where P squared and Q squared represent the frequencies of homozygous genotypes and 2PQ represent the frequency of the heterozygous genotype. So here are Hardy-Weinberg ideal conditions. The 5 conditions for non-evolving populations are rarely met in nature. There must be no mutations, there must be random mating, no natural selection, an extremely large population, and no gene flow to be considered a non-evolving population. Alright, so to apply this Hardy-Weinberg principle, we can assume that the locus that causes PKU is in Hardy-Weinberg equilibrium, given that the PKU gene mutation rate is low, mate selection is random with respect to whether or not an individual is a carrier for PKU allele, natural selection can only act on rare homozygous individuals who do not follow dietary restrictions, the population is large, and migration has no effect as many other populations have similar allele frequencies. Alright, so the occurrence of PKU is 1 per 10,000 births. So Q squared is 0.0001, or Q would be 0.01. The frequency of normal alleles is 0.99. So P equals 1 minus Q. So 1 minus Q being 0.01 is P equals 0.99. The frequency of heterozygotes, or carriers, is 2PQ. So 2 times 0.99 times 0.01 equals 0.0198, or approximately 2% of the U.S. population. We're going to stop here because I want you to take your time in digesting that Hardy-Weinberg. Go back and look at the equations, write them down, tinker with them. I've uploaded a few practice problems from um, Kansas State. They are college level problems. This is also comparative to a college level course, so they should be something that you can accomplish. I've also uploaded a crash course and a Khan Academy video working through these Hardy-Weinberg problems so that you can see some examples being worked. We will have discussion on Friday, so if you have any questions, please make a list and let me know. Make sure to be working through your checkpoint questions, as these will be factored into your next grades. As always, let me know if you have any questions, and make sure to do your readings. Thank you. Bye, guys.